All right, so based off of your closing on Monday, some of you needed a little bit more assistance with these theorems. And so this is, if you're still kind of confused and want some help working with these theorems, or if you missed something, or if you're just crazy, I don't know. So if a line is tangent, I broke it already, tangent to a circle, then the line is perpendicular to the radius. So this is helpful to know because when we get to something like practice problem number 1, the only way I can solve it is knowing that that's a right angle. So this is my tangent line, and then this is my radius. So those two lines are going to be perpendicular. And then in your problem, it says that AC is 25. So this is 25, so you can do a squared plus b squared equals c squared. And then that's how you solve that problem. On the second one, if these lines are tangent, ML and MN, so this is a tangent line, this is a tangent line, that means it touches here. And then we know this is a radius because it goes from the center to the edge. That means these two are right angles. Now we have formed a quadrilateral here, and you should know that all quadrilaterals are 360 degrees. And we know this angle 117, and then these two are both 90. So we add those all up, subtract from 360, and that is how x is 63. This one over here was 20, by the way, if you're checking as you go. Problem 3. When the question's asking if it is tangent, essentially it wants to know, is this a right angle or not? And because of our Pythagorean theorem, we can use that to help us prove it. So we can do a squared plus b squared equals c squared. And if this truly does equal this, that means this is a right triangle and it is tangent. If it doesn't equal that, then it's not a right triangle and it's not tangent. And in this case, when you do 20 squared plus 44 squared, it does not equal 52 squared. And so it is not tangent because it does not make a right angle for that reason. Practice problem number 4 is a little bit tricky. It wants to know the distance between the centers. So it wants to know this distance right here. When you make this shape, this is a right trapezoid. You have typically seen them like this. And that's your right trapezoid. That's the way that's the orientation that we like to look at them. But this one's just turned sideways. So if you go like this, and you make this a rectangle, then this part would be 35, and this part is 8, so this part is 8. If this part up here is 8, and this whole side is 14, that means this part is only 6. So now I have a right triangle that's 35, 6, and then the distance that I'm looking for. So that is how we solve for x there. We turn this into a rectangle and a triangle, and then we solve for the hypotenuse of the triangle. Moving forward, theorem 12.3. Two segments tangent to a circle from a point outside the circle are congruent. So when you have tangent lines, like this is a tangent line and this is a tangent line, the parts outside the circle are congruent. So then these two would be congruent, and then these two would be congruent, and then these two would be congruent. So the parts that make a point are the same. So now we just need to work backwards. If this is 5, this part has to be 5. From our information here, GE is 9. So this whole thing's 9, CE is 8, and GJ is 7. So this part's 5 because this is 5. If this is all 9, this has to be 4. This has to be 4 because that's 4. If that's all 7, this has to be 3. Those have to be the same. Then this is 5, so this has to be 3 so that it's 8. So that has to be 3. So this is 6. Oops. So then our side lengths are 7, 9, 8, and 6. And then when you add those all together, then you get 30. The corollary part over here, corollary is just kind of like an addition to what you're talking about. The line through an external point and the center of a circle bisects the angle formed by two tangent segments. So all that means is that AC is going to bisect this angle. Then from our information, the radius is 39. So both of those would be 39. Based on this, the previous theorem, if this part's 80, then this part has to be 80. So AB is 80, CB is 39, AC is this part of a triangle. Since these are right angles, then we just have a Pythagorean theorem problem to solve. We have 39 squared plus 80 squared equals c squared. And then you solve all of that to get 89. On to the back. That's the front again. Keep scrolling. On to the back. Congruent central angles will have congruent arcs and congruent chords. So we did talk about this a little bit more in class than the others. So this chord and this chord would be the same because they both have to do with this 30-degree angle, which means this arc and this arc are also the same, again, because of the central angle being the same. This chord and this chord would be the same because those both have to do with 50 degrees, as well as the arcs associated with them. And then we can even go so far to say this part that's 130 goes with this part that's 130 and goes with this part that's 130. So those are all congruent arcs as well. And then the congruent chords that are associated with those also. So really just if you can add them all together and they equal the same thing, there you go. They do have to be next to each other though. So I couldn't add this 30 to this 20. It doesn't work that way. It still has to be adjacent to each other. The fifth one, congruent chords are equidistant. This is pretty self-explanatory. So those would be congruent and those would be congruent. These are two diameters. Diameters of a circle are always congruent. They're the same distance from the center as they're both passing through it. This example, this is 8 away and this is 8 away, so those are congruent chords. This, my two different numbers, tells me that they're not. This, I have no idea how far away these two things are. They might be the same, but because it doesn't tell me, I cannot assume. So we cannot determine if those are congruent or not from the given information. And then finally, in a circle, a radius that is perpendicular to a chord bisects the chord and its arcs. So these two pieces are the same, and then these two arcs are the same because it says it's bisecting that, which means this is perpendicular. So if PI is 8, then each of these is only 4. And then TN is 3. So we're trying to find NR, which is this part, and we're trying to find TP, which is this part. So for TP, we've made this right triangle. This was 4 and this was 3, so we find that part. So you can do Pythagorean theorem for that, and that's 5. So TP is 5. And what you need to notice about TP is that it's a radius of the circle, which means this is a radius, and this is a radius, and this is a radius, and this is a radius. So any radius is going to be 5. So because this is 5, and we know Tn, this little part, is 3, that means NR has to be 2 in order to complete the whole 5. And then finally, problem 11, OR is 25, OL is 7, and we're trying to find CL and then CA. So we need to know that that's double because these are going to be the same because those are perpendicular, and that's the whole purpose of our theorem. So again, like on the last problem, knowing that all the radiuses would be the same, this is going to be 25 also. So because we know OR, we can now assume that OC is also 25. And now we have this right triangle to do 7 squared, 25 squared, and we're looking for that. So it really turns into 25 squared minus 7 squared equals x squared to get the value of CL, which turns out to be 24, and then CA is double at 48. So that was kind of quick, but if you still have a question about something, please ask. Otherwise, I hope that cleared up some misunderstandings.